Before going on, we'll have a little detour to discuss finite objects, systems of objects, and their centre of mass. We've formally limited the syllabus of this course to particles, objects small enough that we can represent their position with a point. But for objects of finite size, what point would we use? The end of this stick has a complicated path. But is there a point in the stick that traces out the parabolic path that we studied in projectile motion? Yes, there is such a point, and it's called the centre of mass. Here's a neat trick. Provided that the gravitational field is uniform, the centre of mass is the same as the centre of gravity, or the balance point. For this stick, from symmetry, the centre of mass lies on its axis, and it's at the point where it balances. So let's label it. Now we see that the centre of mass traces out a parabola. The centre of mass behaves like a particle. So, for a finite or extended object, Newton's second law is just total external force equals mass times the acceleration of the centre of mass. What about the centre of mass of two or more objects? Where is the centre of mass of these two objects? Obviously, the balance point is going to be closer to the larger mass. Treat these two cars as a system and suppose that they have equal mass. So the centre of mass is halfway in between them. If their initial speeds are equal, the centre of mass is stationary and it remains stationary afterwards. This is an important application of Newton's second law, or conservation of momentum. If the total external force has negligible impulse, then the velocity of the centre of mass is unchanged during a collision. With the air track, we reduce friction almost to zero, and I'll use two sliders that have the same mass. So the centre of mass is halfway between them. Here I put putty on one so that they stick together in a collision. I want you to imagine what the centre of mass will do after the collision. And what about this case? And this one? Okay, make your predictions.